The night sky gives you a powerful illusion. Thousands of stars scattered across a black canvas. The Milky Way stretched overhead like a glowing river. Everything about that view suggests abundance, density, fullness. It feels as though the universe is crowded, packed with light, leaving little room for emptiness. That impression is deeply misleading. When astronomers step back far enough, hundreds of millions of light years, the familiar image collapses. On the largest scales, the universe is not a sea of stars. It is a landscape dominated by absence. More than 80% of the universe's volume consists of regions that contain almost nothing at all. These regions are known as cosmic voids. Empty here does not mean philosophical nothingness. It means something more unsettling. Vast expanses where galaxies are rare, where gas is thin, where matter that emits light is almost entirely missing. Entire clusters of galaxies occupy only the edges of these regions, outlining bubbles of near-nothingness that stretch across unimaginable distances. To grasp how extreme this is, imagine shrinking the entire Milky Way, its hundreds of billions of stars down to the size of a grain of sand. The next grain would not be sitting beside it. It would be hundreds of meters away, and the space between those grains would not be filled with more sand, but with air so thin it is almost irrelevant. That is what the large-scale universe looks like. What shocks astronomers is not that galaxies exist, but how little space they actually occupy. Nearly all the matter we are familiar with, stars, planets, glowing gas, is compressed into narrow filaments and dense knots. The overwhelming majority of space lies between them, dark and quiet. Human intuition struggles with this because everyday experience trains the mind to focus on what is present. We notice buildings, people, objects. Empty space fades into the background. But the universe reverses that logic. On cosmic scales, emptiness is not the background. It is the dominant feature. For much of scientific history, this was not how the cosmos was imagined. Early models assumed matter would be spread more or less evenly, with gravity creating gentle variations. When astronomers began mapping the distribution of galaxies in the late 20th century, they expected a fog thicker in some places, thinner in others. Instead, they found holes, enormous holes, regions hundreds of millions of light years across containing almost no galaxies at all. These voids were surrounded by thin walls and filaments of matter, giving the universe the appearance of a sponge or a foam rather than a cloud. The initial reaction was not celebration, but suspicion. Something this strange had to be wrong. Maybe the surveys were incomplete. Maybe faint galaxies were being missed. Maybe the algorithms that reconstructed three-dimensional maps were creating artificial gaps. Astronomers checked, rechecked, and checked again. The voids remained, with better instruments, deeper surveys, and more sophisticated analysis. The picture only became clearer. The universe was not smoothly filled. It was structured around emptiness. This realization forced a quiet shift in perspective. Galaxies were no longer the primary architecture of the cosmos. They were decorations along the edges of something larger. The true skeleton of the universe was defined by what was missing, not by what was present. Seen this way, the bright structures we admire, spiral galaxies, glowing clusters, are like the edges of bubbles in a cosmic foam. The bubbles themselves are the voids, and they dominate the volume. The reason this feels so counterintuitive is simple. We observe the universe from inside one of those rare, dense regions. Living inside a galaxy is like standing in the middle of a city and concluding that Earth is covered in buildings. From that perspective, emptiness seems like an exception. From a cosmic distance, density is the exception. Human perception is poorly equipped to deal with astronomical scales. The brain evolved to navigate meters, not megaparsecs. Faced with distances measured in millions of light years, It compresses everything into a manageable mental picture. In doing so, it erases the vastness of the gaps. If your eyes could truly see the large-scale universe, the dominant visual would not be stars. It would be darkness, broken occasionally by faint, thread-like structures tracing the edges of enormous empty regions. This matters for more than aesthetics. If most of the universe is empty, then the behavior of the universe cannot be understood by studying only its crowded parts. Expansion, gravity, and the flow of light all behave differently in regions where matter is scarce. The voids are not passive. They influence how the cosmos evolves. Light traveling through emptiness experiences less gravitational distortion than light passing near dense regions. The expansion of space itself can proceed differently, where matter offers little resistance. Even the way we measure cosmic distances can be subtly affected by how much empty space lies along the line of sight. In other words, emptiness becomes a physical actor. For centuries, astronomy focused on luminous objects because that was all we could see. Stars, nebulae, galaxies. These were the clues available. But as our maps grew larger and more precise, it became impossible to ignore the silent majority of space surrounding them. Understanding the universe now requires taking nothing seriously. It requires studying regions with almost no galaxies, almost no gas, and almost no light, and asking how these vast voids shape everything around them. This is not an intuitive leap. It challenges the instinct to equate importance with visibility. It asks science, and by extension, humanity, to accept that absence can be just as influential as presence. When you look up at the night sky after grasping this idea, the experience subtly changes. The stars no longer represent a crowded cosmos. They become rare islands of matter suspended in an ocean of darkness. The blackness between them is no longer an empty backdrop. It is the dominant environment in which all cosmic stories unfold. The universe appears full. In reality, it is overwhelmingly empty. And that emptiness is not a flaw in the cosmic design. It is the framework that gives the universe its shape. For most of human history, the universe had no map. There were star charts, constellations, and catalogues of bright points on the sky, but no sense of large-scale structure. Astronomers knew where stars appeared, not how matter was arranged in 3 dimensions. The cosmos was flat, painted on a dome, its depth guessed rather than measured. That changed when distance finally entered the picture. In the early 20th century, astronomers learned how to measure how far galaxies were, not just where they appeared. By the late 1970 seconds and early 1980 seconds, this capability matured into something revolutionary: redshift surveys. Instead of simply counting galaxies, scientists began measuring their distances and plotting their positions in space. At first, the goal was modest: map where galaxies are, see whether matter thins out gradually with distance, confirm that the universe looks roughly the same in all directions. The result was anything but modest. One of the earliest breakthroughs came from the Center for Astrophysics Redshift Survey, often called the CFA survey. Using telescopes in Arizona, astronomers measured the redshifts of thousands of nearby galaxies and plotted them in wedge-shaped slices of space. When the first plots appeared, they were deeply unsettling. Instead of a smooth distribution, the galaxies traced thin arcs, walls, and filaments. Between these structures were enormous blank regions, vast volumes with almost no galaxies at all. The empty regions were not small gaps. Some spanned tens of millions of light years. At first, many researchers assumed something had gone wrong. The data looked too strange. The human brain is excellent at finding patterns, even where none exist. Were these voids simply artifacts of incomplete sampling? Were faint galaxies being missed? Was the survey geometry creating illusions? To address these doubts, astronomers expanded the maps. In the late 1980s, Margaret Geller and John Huckra produced what became known as the slice of the universe. This iconic visualization showed galaxies arranged along sweeping curves, enclosing enormous empty spaces, like cells in a cosmic honeycomb. The voids were undeniable. One of the most famous early discoveries was the Boötes void, a region roughly 250 million light-years across, containing almost no galaxies. In a universe filled with hundreds of billions of galaxies, finding a volume that large, nearly empty, felt absurd. And yet, it was real. As more surveys confirmed the pattern, skepticism gave way to a deeper question. How could such vast, empty regions form at all? Gravity pulls matter together. Intuition suggests it should leave behind smaller gaps, not colossal cavities. The answer lay in the early universe. Tiny density variations present shortly after the Big Bang. Differences of just 1 part in 100,000 were amplified by gravity over billions of years. Regions slightly denser than average pulled in more matter, growing into filaments and clusters. Regions slightly less dense lost matter to their surroundings, becoming emptier with time. Voids did not appear because something was removed. They appeared because matter flowed away. As mapping techniques improved, the scale of this structure became even clearer. Surveys expanded from thousands of galaxies to hundreds of thousands, then millions. Each new map sharpened the same image, a universe shaped like a web. The most influential of these projects was the Sloan Digital Sky Survey. Beginning in the early 2000s, SDSS transformed cosmology by charting the positions of millions of galaxies across a huge volume of space. When the data were visualized, the pattern was unmistakable. Filaments stretched for hundreds of millions of light-years. Clusters sat at their intersections, and between them lay vast voids, dominating the cosmic volume. What made these maps so powerful was not just their size, but their statistical rigor. With enough galaxies, astronomers could quantify emptiness. They could measure void sizes, shapes, and distributions. Emptiness became something you could analyze, not just observe. This marked a turning point. Before these surveys, voids were curiosities, odd features on unusual plots. Afterward, they became central to cosmology. Any successful theory of the universe now had to explain not only where galaxies are, but why most of space contains so few of them. The maps also delivered a humbling lesson about perspective. From Earth, the sky feels crowded. Stars overlap. Galaxies blur into patches of light. But the maps revealed that this sense of density is local, not universal. We live inside one of the rare dense regions. Most of the cosmos looks nothing like our neighborhood. The early redshift maps did more than expose emptiness. They changed how astronomers thought about structure itself. The universe was no longer described as matter sprinkled through space. Space itself became the stage, shaped by where matter had fled. Even the language of cosmology shifted. Scientists began speaking of walls, filaments, nodes, and voids, terms borrowed from architecture and biology. The cosmos resembled a living network more than a static distribution. Crucially, these maps also set limits. The voids were enormous, but not infinite. Their sizes and spacing followed predictable patterns consistent with gravity acting over billions of years. This consistency reassured astronomers that the voids were not signs of chaos, but of an underlying order. The discovery of voids also reshaped observational strategy. Instead of avoiding empty regions as uninteresting, astronomers began targeting them. Voids became laboratories for testing gravity, dark matter behavior, and cosmic expansion under extreme conditions. All of this began with simple maps points plotted in space. Those first surveys did not answer every question. They raised far more than they resolved. But they achieved something more important. They forced science to acknowledge that the universe is defined as much by what is absent as by what is present. Once the voids were seen, they could not be unseen. The maps revealed a universe whose most common feature is emptiness, and whose luminous structures exist only because matter was pushed out of vast regions long ago. The great voids were not mistakes in the data. They were the data, finally telling the truth about the shape of the cosmos. The first reaction to the cosmic voids was not wonder, it was rejection. When early redshift maps revealed vast, empty regions, many astronomers assumed the mistake lay not in the universe, but in the data. The idea that gravity, a force known for pulling matter together, could produce regions hundreds of millions of light years across, with almost no galaxies, felt deeply implausible. The simpler explanation was error. This was not stubbornness. It was scientific discipline. Astronomy has a long history of false discoveries born from incomplete data, instrumental bias, and human pattern seeking. Before declaring something revolutionary, astronomers are trained to exhaust every mundane explanation. And in the case of cosmic voids, there were many places to look for problems. The most obvious concern was selection bias. Early galaxy surveys were limited by brightness. Telescopes could only detect galaxies above a certain luminosity. Faint galaxies, especially small or diffuse ones, could easily be missed. If those faint galaxies filled the apparent gaps, the voids would vanish. Another suspicion involved survey geometry. Many early redshift maps were wedge-shaped slices through space. A poor choice of angles or boundaries could create artificial gaps, optical illusions caused by how data was sampled rather than how matter was distributed. Then there was the issue of cosmic dust. Our own galaxy contains thick lanes of dust that block light from beyond. Large areas of the sky are obscured, especially near the galactic plane. Perhaps the voids were simply regions hidden behind dust, not truly empty. And finally, there was the human factor. Astronomers knew how easily the brain connects dots into patterns. Filaments, walls, bubbles, these could be visual tricks, not physical structures. So the skepticism hardened into a methodical campaign to disprove the voids. The first step was repetition. Independent teams, using different telescopes, different instruments, and different analysis pipelines, began mapping the same regions of space. If voids were artifacts, they should disappear when observed under new conditions. They did not. Next came depth. Surveys pushed farther, probing more distant galaxies. If voids were caused by missing faint galaxies nearby, deeper observations should fill them in. Instead, the emptiness persisted and often grew more pronounced as survey volume increased. Then came completeness tests. Astronomers artificially removed galaxies from dense regions to see if similar patterns emerged. They tested random distributions against observed data. Statistical analyses showed that the voids were highly unlikely to arise by chance or sampling error. Still, discomfort remained. The turning point came when simulations entered the conversation. With increasing computational power, cosmologists began running large numerical simulations of the universe based on known physics, gravity, dark matter, and initial density fluctuations inferred from the early universe. These simulations started from a nearly uniform state and evolved forward billions of years. When the results were visualized, something unsettling happened. The simulations produced voids, not small gaps, but vast, underdense regions surrounded by filaments and clusters, structures strikingly similar to those seen in observational maps. The voids were not anomalies. They were a natural outcome of gravitational evolution. This changed the tone of the debate. If both observation and theory were pointing to the same structures, the burden of proof shifted. The question was no longer whether voids existed, but whether astronomers had underestimated how efficiently gravity could evacuate regions of space. Yet even then, caution prevailed. Some researchers argued that while voids might exist, their apparent size could still be exaggerated by observational effects. Light from distant galaxies passes through intervening structures, gravitational lensing, redshift distortions, and peculiar velocities could stretch or compress structures along the line of sight. So astronomers refined their tools again. They corrected for redshift space distortions. They accounted for galaxy motions relative to the cosmic expansion. They cross-checked results using different traces of matter, including galaxy clusters and intergalactic gas. Each correction made the maps cleaner. The voids remained. What made this episode particularly revealing was how uncomfortable it made the community. Cosmic voids challenged a quiet assumption that matter, even when clumped, should still leave behind a relatively filled universe. Instead, the data suggested a cosmos where emptiness dominates by design, not accident. There was also a psychological barrier. Galaxies are easy to respect. They shine, they rotate, they explode. Voids do none of these things. They are silent. Assigning physical importance to something defined by absence felt almost philosophically wrong, but science does not reward comfort. As evidence accumulated, the language changed. Papers stopped asking whether voids were real and began asking how to define them precisely. Algorithms were developed to identify void boundaries. Researchers debated how empty was empty enough to qualify. The debate moved from denial to classification. This transition marked a subtle but important shift in cosmology. It showed how the field adapts when reality refuses to match intuition. Instead of forcing observations to fit expectations, expectations were rewritten. The voids also exposed the limits of observational humility. Astronomers realized that for decades, they had been staring at the bright parts of the universe and assuming they told the whole story. The data had always hinted at emptiness. But without three-dimensional maps, that hint was easy to ignore. Once depth was added, the illusion shattered. By the early 2000s, the idea that the universe contained vast voids was no longer controversial. It was foundational. Any serious model of large-scale structure had to reproduce them. What remained controversial was their significance. Were voids passive leftovers, or active players in cosmic evolution? Did they merely reflect where matter was not? Or did they influence how space itself behaved? Those questions would take years to unfold, but the episode left a lasting lesson. The greatest resistance in science often arises not when data is noisy or ambiguous, but when it is clear and deeply counterintuitive. The voids were not subtle. They were enormous. Their crime was not uncertainty, but contradiction. In the end, astronomers accepted the uncomfortable conclusion. The data was not wrong. The universe was not broken, just stranger than expected. The great voids were not errors waiting to be corrected. They were warnings, quiet reminders that the cosmos does not owe us familiarity, and that sometimes the most important discoveries emerge precisely where we least expect to find anything at all. At first glance, a cosmic void sounds simple. A region of nothing. No galaxies, no stars, no light. An astronomical blank space written off as absence. That description is convenient and wrong. In physics, nothing has never meant empty in the everyday sense. Even the most rarefied regions of the universe contain structure, activity, and influence. The surprise is not that voids are empty, but that they are far more complex than their name suggests. To begin with, cosmic voids are not completely devoid of matter. They contain far less matter than average, but not zero. Thin wisps of gas stretch across them. Isolated dwarf galaxies drift quietly within them. dark matter, invisible but gravitationally real, still permeates these regions, albeit at much lower density. If you could travel through a void, it would not resemble a perfect vacuum. It would resemble an extreme version of intergalactic space, cold, sparse, and quiet but still governed by physical laws. This distinction matters because in cosmology, empty does not mean irrelevant. Even in the deepest voids, gravity still operates, not strongly, not violently, but persistently. Matter inside voids still feels the pull of surrounding structures. Over billions of years, this gentle imbalance causes what little matter exists to drift outward, slowly evacuating the region even further. Voids, in other words, are not static holes. They are dynamic environments, evolving over cosmic time. There is also something more subtle at play: fields. Modern physics describes reality not as a collection of objects floating in emptiness, but as fields filling all of space. The electromagnetic field, gravitational fields, quantum fields. These do not switch off just because matter is sparse. In a void, quantum fields still fluctuate. Energy still exists in the vacuum. Space itself still has properties: stretching, curvature, and dynamics that respond to the overall content of the universe. This is where intuition begins to fail completely. A region, toggle. In everyday language, nothing is inert. In cosmology, nothing is active. Void regions expand faster than dense regions, not because something is pushing them outward, but because there is less gravitational resistance slowing expansion down. Where matter is scarce, space stretches more freely. This makes voids some of the most extreme environments for studying cosmic expansion. They exaggerate behaviors that are subtle elsewhere, and light notices this. Photons passing through voids experience a different gravitational landscape than those skimming clusters of galaxies. They lose and gain energy differently. Over immense distances, these tiny effects accumulate, subtly altering the information light carries to us. This means voids leave fingerprints on observations, even though they emit almost no light of their own. There is also the question of dark matter. Although voids contain far less dark matter than dense regions, they still contain some. And because dark matter dominates the mass budget of the universe, even a thin distribution matters. Its gravitational influence shapes how voids evolve, how their boundaries sharpen, and how surrounding filaments grow. Voids are not carved out of nothingness. They are sculpted by the slow redistribution of matter under gravity. Then there is time. Void interiors are some of the oldest regions of the universe, in a very specific sense, because little happens there. They preserve information about early conditions more cleanly than violent. Crowded regions, clusters undergo mergers, star formation, feedback, and chaos. Voids evolve gently. This makes them cosmic archives. Studying voids allows astronomers to test theories of gravity and expansion in environments largely free from astrophysical complications. Fewer stars, fewer explosions, fewer confounding variables. Ironically, the emptiest places may offer the clearest insights. Another misconception is that voids are uniform. They are not. Some are relatively shallow, slightly underdense regions surrounded by mild structures. Others are deep, extreme cavities with almost no galaxies at all. Some merge with neighboring voids, forming even larger empty regions. Voids have substructure. Even nothing has texture. As surveys improved, astronomers began to classify voids by size, depth, shape, and environment. Some are round, others elongated. Some sit between massive superclusters, others exist in quieter regions of the cosmic web. Each type tells a different story about how matter flowed in the past. Perhaps the most counterintuitive realization is this: voids help define what galaxies become. Galaxies near void edges experience different growth histories than those in dense clusters. They form stars differently. They interact less. Their evolution is shaped not only by what surrounds them, but by what does not. Absence becomes an environmental factor. This flips a long-standing assumption in astronomy. Environment was once defined purely by proximity to matter. Now, distance from matter matters just as much. From a philosophical perspective, this is unsettling. We prefer to assign importance to things we can see and touch. Voids resist that instinct. They matter precisely because they are defined by scarcity. But physics has no preference for intuition. If space expands differently in emptier regions, if light behaves differently there, if gravity reveals new behaviors under minimal influence, then voids are not footnotes. They are laboratories, and they force a deeper reconsideration of what it means for something to exist in the universe. The idea that nothing contains fields, energy, motion, and influence challenges the everyday meaning of emptiness. It suggests that the universe is not built from objects placed into space, but from space itself, structured, dynamic, and active. Cosmic voids are not holes punched into reality. They are part of reality's design. They show that absence can have shape, that silence can have structure, that regions defined by what they lack can still determine how the universe behaves. When astronomers speak of voids now, they no longer mean nothingness. They mean an extreme state of the cosmic environment, one that reveals physics more clearly by stripping away clutter. In the end, nothing turns out to be one of the most informative things the universe has to offer. When astronomers describe cosmic voids as empty, they are careful with their words. Empty of galaxies, empty of stars, empty of glowing gas, but not empty of mass. The quiet presence inside these vast regions is dark matter, the dominant form of matter in the universe, invisible to telescopes, yet unavoidable in its effects. Even where almost nothing shines, dark matter remains, thinly spread, shaping the evolution of emptiness itself. This idea is counterintuitive. Dark matter is often introduced through dramatic scenes, galaxies rotating too fast, clusters bending light, vast halos anchoring luminous matter. It is associated with gravity at its strongest. Voids, by contrast, feel like places where gravity has retreated. The truth sits in between. Dark matter does not vanish in voids. Its density drops, sometimes to a fraction of the cosmic average, but it never reaches zero. And because dark matter outweighs ordinary matter by roughly 5-1, even a sparse distribution still matters. To understand why, it helps to rethink what dark matter actually is, not a substance that clumps only in spectacular places, but a component woven into the fabric of the universe from the beginning. In the early universe, matter was nearly uniform. Dark matter and ordinary matter were mixed together, differentiated only by how they interacted. Over time, gravity amplified tiny differences in density. Where dark matter was slightly denser, it pulled in more matter. Where it was slightly thinner, matter drained away. Voids are the natural outcome of this process. They are not regions where dark matter was removed. They are regions where dark matter never accumulated efficiently. As denser areas grew denser, underdense regions grew emptier by comparison. Dark matter flowed outward, feeding the filaments and clusters that define the cosmic web. What remained inside voids was a diluted shadow of the original distribution. This slow evacuation has consequences. Inside a void, the gravitational pull toward surrounding structures creates a gentle outward flow. Galaxies near void centers drift away over billions of years. Gas thins. Star formation slows or never begins. The region becomes quieter with time. Dark matter orchestrates this process silently. It does not shine. It does not collide. It simply responds to gravity, and gravity responds to it. One of the most revealing insights from simulations is that voids are dark matter structures first, luminous structures second. When cosmologists model the universe using only dark matter and gravity, voids still appear nearly identical in size and shape to those observed. This tells us something fundamental. Galaxies trace dark matter, not the other way around. The visible universe is a thin layer painted over a much deeper gravitational scaffold. In voids, that scaffold is sparse but present, like faint lines beneath a blank page. Dark matter also determines how voids grow. As surrounding filaments and clusters pull matter toward them, void interiors expand, not explosively, but steadily. The boundaries of voids sharpen. Their centers become emptier. Smaller voids merge into larger ones, creating a hierarchy of emptiness. This merging process is the mirror image of galaxy mergers. Instead of structures colliding, absences combine. And at every stage, dark matter sets the pace. Because voids are underdense, they provide a unique environment to test dark matter behavior. In crowded regions, interactions are complex. Baryonic physics, gas cooling, star formation, feedback introduce chaos. In voids, these effects are minimal. What remains is gravity in near isolation. This makes voids ideal laboratories. If dark matter behaves differently from standard assumptions, if it interacts weakly with itself, decays, or has unusual properties, those differences may be easier to detect where ordinary matter does not dominate. Subtle deviations in void shapes, growth rates, or internal motions could point to new physics. Another critical role of dark matter in voids involves boundaries. The edges of voids are not soft transitions. They are often sharply defined walls of matter where dark matter density rises rapidly. These walls act as gravitational barriers, influencing how galaxies move and how light propagates. Photons traveling from distant galaxies pass through alternating regions of high and low dark matter density. Each transition imprints a tiny effect on their energy. Over cosmic distances, these effects accumulate. Void interiors, being dominated by low dark matter density, leave distinct signatures on large-scale observations. Ignoring them can bias measurements. This becomes especially important when measuring cosmic expansion, because voids expand faster than denser regions. Light that travels predominantly through voids can suggest a different expansion history than light passing near clusters. Dark matter, by shaping the distribution of voids, indirectly shapes how we infer the behavior of the entire universe. The emptiest regions, paradoxically, may amplify certain cosmological signals. There is also a quieter implication. Dark matter inside voids evolves more gently than in dense regions. It experiences fewer mergers, fewer violent rearrangements. In this sense, void dark matter preserves a memory of early cosmic conditions more faithfully than matter in clusters. Clusters are turbulent. Voids are calm. This makes voids valuable for studying the initial seeds of structure laid down shortly after the Big Bang. The imprint of those early fluctuations is less disturbed inside emptiness. It is tempting to imagine voids as failures of structure formation, places where the universe did not finish the job. But that interpretation misses the point. Voids are not unfinished. They are fully realized outcomes of gravitational evolution. Dark matter did exactly what gravity told it to do. From a broader perspective, this reframes how importance is assigned in cosmology. Dark matter is not important only where it piles up dramatically. It is equally important where it barely accumulates at all. Its absence is as informative as its presence. In voids, dark matter teaches restraint. It shows how the universe organizes itself, not by filling every region with equal enthusiasm, but by creating contrast dense against sparse, bright against dark, active against quiet. The cosmic web depends on this contrast. Without underdense regions, there would be no filaments. Without emptiness, there would be no structure to outline. And at the heart of that contrast lies dark matter, shaping both the crowded cities of galaxies and the vast deserts between them. Even in the deepest voids, where stars are rare and light is faint, gravity still whispers. Dark matter listens, and over billions of years, that quiet conversation defines the largest structures the universe will ever build. Gravity is usually introduced as a dramatic force. It pulls stars into orbits, crushes matter into black holes, binds galaxies into clusters. In textbooks and documentaries alike, gravity announces itself through violence and spectacle. But in the emptiest regions of the universe, gravity does something far stranger. It whispers. Inside cosmic voids, gravity does not disappear. It simply loses its usual intensity. There are fewer masses to pull on each other, fewer collisions, fewer dramatic events. What remains is gravity in its most patient form, slow, cumulative, and almost invisible on human timescales. This is where intuition misleads again. It is tempting to imagine voids as places where gravity has failed, where it no longer matters. In reality, voids are shaped precisely because gravity has been working continuously for billions of years. The key difference is imbalance. In dense regions, gravitational pulls compete in many directions. Forces cancel, clash, and rearrange matter chaotically. In low-density regions, gravity has fewer players. The dominant pull comes from the surrounding structures, the filaments and clusters that border the void. This creates a subtle but persistent gradient. Matter inside a void feels a net pull outward, away from the center and toward the denser edges. Over cosmic time, this causes voids to slowly expand, not explosively, not uniformly, but inexorably. The emptier a region becomes, the weaker gravity is inside it, and the easier it is for space itself to stretch. Voids are not carved out by some repulsive force. They are evacuated by gravity's uneven distribution. This evacuation process is astonishingly slow. A galaxy drifting inside a void might move only a few tens of kilometers per second relative to the cosmic expansion. On human scales, that is nothing. On cosmic scales, over billions of years, it is enough to reshape the universe. Gravity does not rush. This slowness is precisely what makes voids valuable. In dense environments, gravitational effects are tangled with astrophysical noise, star formation, supernova explosions, black hole feedback. In voids, those complications are minimal. What remains is gravity operating almost alone. This allows cosmologists to study gravity in a regime that is otherwise inaccessible. One surprising consequence of this regime is how space itself behaves. In general relativity, gravity is not a force acting within space. It is the curvature of space and time, where mass energy is scarce. Space-time curvature is weaker. The geometry of the void interior is closer to flat. This has measurable effects. Light traveling through low-density regions experiences less gravitational time delay and less lensing than light passing near clusters. Over long distances, paths through voids become preferred routes, not because they are faster in a simple sense, but because they encounter fewer distortions. In this way, gravity shapes not just matter, but information. Another quiet effect involves velocity fields. Galaxies do not simply sit still and expand with the universe. They have peculiar velocities, motions relative to the overall expansion caused by local gravitational influences, inside voids. These velocities point outward. Galaxies stream away from the center, tracing gravity's long-term evacuation plan. At void boundaries, velocities change direction, responding to the dense walls that enclose them. Mapping these motions reveals the gravitational landscape in 3 dimensions. Voids act like negative mass regions, not because they repel matter, but because everything around them pulls matter away. This negative-like behavior is a geometric illusion, but a powerful one. It highlights how gravity's influence depends not only on what is present, but on what is missing nearby. There is also a temporal aspect. Because gravity is weaker inside voids, structures evolve more slowly there. Small galaxies form later. Interactions are rarer. Mergers are infrequent. In this sense, voids are time capsules, regions where cosmic evolution has been delayed. This delay matters when testing cosmological models. If gravity behaves differently than expected on large scales, those differences may show up most clearly where gravity is weakest. Voids amplify subtle deviations. This has led some researchers to use voids as precision tools. Instead of studying where gravity is strongest, they study where it is barely strong enough. The logic is simple. If gravity deviates from theory, it is easier to spot when the signal is not drowned out by complexity. Even alternative theories of gravity often predict their strongest effects in low-density environments. In dense regions, modifications are screened or suppressed. In voids, they are free to act. Once again, emptiness becomes a laboratory. Gravity's quiet work also shapes void boundaries. As matter flows outward, void edges sharpen. The contrast between empty interiors and dense walls increases. Over time, this leads to a universe with increasingly pronounced structure. The cosmic web becomes more skeletal, filaments thinner, voids larger. This progression is not accidental. It reflects gravity's tendency to amplify differences. Slightly denser regions grow denser. Slightly emptier regions grow emptier. Gravity rewards imbalance. From a philosophical perspective, this is unsettling. Gravity is often imagined as a unifying force, pulling everything together. On cosmic scales, it is also a separating force, organizing matter into islands and leaving vast oceans between them. It creates togetherness and isolation at the same time. There is a quiet elegance in this process. No explosions are required. No exotic forces are invoked. Gravity works slowly, consistently, almost indifferently. Given enough time, it sculpts the largest patterns the universe will ever know. And time is something the universe has in abundance. Billions of years pass without fanfare. Galaxies drift. Voids breathe outward. Light crosses empty space, carrying subtle clues about the terrain it has traversed. From our position inside a dense region, these processes are easy to overlook. They do not announce themselves. They leave no immediate trace in the night sky, but they are always underway. Gravity's quiet work reminds us that not all power is loud. Some of the most influential forces operate at the edge of perception, shaping reality without spectacle. In the low-density spaces between galaxies, gravity does not rest. It refines, it separates, it defines the negative space that gives the universe its form. And in doing so, it proves that even where matter is scarce, physics is still at work, patient, precise, and relentless across the longest timescales imaginable. The cosmic web did not appear fully formed. It was not woven deliberately, strand by strand, into the vast architecture we see today. It emerged gradually, almost reluctantly, from a universe that began in a state of near-perfect simplicity. In the beginning, matter was spread with extraordinary uniformity. Shortly after the Big Bang, the universe was hot, dense, and remarkably smooth. Tiny fluctuations existed, differences in density no larger than 1 part in 100,000, but on average, everything looked the same everywhere. Those imperfections were insignificant by everyday standards. By cosmic standards, they were destiny. Gravity does not need large differences to act. It only needs imbalance. Where matter was ever so slightly denser than average, gravity pulled inward. Where matter was slightly less dense, gravity pulled outward toward those denser regions. Over time, these minute differences were amplified. The dense regions grew denser. The sparse regions grew emptier. This slow amplification is what seeded the cosmic web. At first, matter flowed gently. There were no galaxies, no stars, no structures recognizable to modern eyes. But gravity worked continuously, sculpting the distribution of matter into sheets and filaments. These sheets intersected, forming nodes, the future homes of galaxy clusters. Between them, voids began to open. The process was not explosive. It was patient. Over hundreds of millions of years, matter drained from underdense regions and accumulated along narrow paths. These paths grew more pronounced with time, becoming the filaments that now stretch across hundreds of millions of light years. The web was born not by construction, but by evacuation. Computer simulations reveal this process with unsettling clarity. Starting from an almost featureless early universe, gravity alone, acting primarily through dark matter, produces a network nearly indistinguishable from what we observe today. Filaments emerge naturally. Clusters form at intersections. Vast voids dominate the volume. Nothing extra is required. This realization reshaped cosmology. The large-scale structure of the universe was no longer a mystery requiring exotic mechanisms. It was the inevitable outcome of simple laws applied over immense time. Yet inevitability does not mean simplicity. The cosmic web is not a regular grid. It is irregular, asymmetric, and hierarchical. Filaments vary in thickness. Clusters differ in mass. Voids merge and grow. The structure evolves continuously. Even now, what makes the web remarkable is its scale. Individual galaxies span tens of thousands of light years. Filaments can stretch for hundreds of millions. The web links regions so vast that light itself takes eons to cross them. This is structure on the largest scale possible without collapsing under its own gravity, and it all traces back to those tiny, early fluctuations. The cosmic microwave background, the afterglow of the early universe, preserves a snapshot of those primordial irregularities. The same patterns seen faintly imprinted in that ancient light reappear billions of years later as the cosmic web. This continuity is profound. It shows that the universe's largest structures are direct descendants of its earliest moments. The web also reveals an important truth about gravity's behavior over time. Gravity is not content to merely pull matter together locally. Given enough time and space, it organizes matter globally, creating coherence across distances that defy intuition. The filaments are not accidents. They are highways along which matter flows. Gas streams along these filaments toward clusters, feeding galaxy growth. Dark matter defines their shape and stability. Even today, the web channels material across cosmic distances, sustaining the slow evolution of structure. Voids, meanwhile, play an equally crucial role. As filaments thicken, voids expand. As matter drains away, emptiness becomes more pronounced. This mutual reinforcement sharpens the contrast of the web. Structure and absence co-evolve. The web is therefore not just a map of matter, but a record of motion. Every filament marks the path matter has taken. Every void marks where matter has fled. This dynamic history challenges the static images often used to represent the universe. The cosmic web is not frozen. It is alive with slow movement, stretching and reshaping as expansion and gravity compete. Expansion tries to pull everything apart. Gravity tries to pull matter together. The cosmic web is the compromise between these two tendencies. On smaller scales, gravity wins, galaxies form, clusters bind. On the larger scales, expansion dominates, preventing the web from collapsing into a single mass. Between these extremes lies the intricate network we observe. The emergence of the web also reframes how emptiness is understood. Voids are not empty leftovers between structures. They are integral components of the same process. Without voids, filaments would not stand out. Without filaments, voids would have no boundaries. Structure requires contrast. There is a quiet elegance in this outcome. The universe does not maximize uniformity or chaos. It settles into patterns that reflect the interplay of simple rules applied relentlessly over time. From a human perspective, the cosmic web evokes mixed emotions: awe at its scale, humility at our smallness, unease at the realization that even the grandest structures are transient on cosmic timescales. Filaments will thin, voids will grow, clusters may eventually drift apart as expansion accelerates. The web itself is a phase, not a final state, yet it is the phase we inhabit. Every galaxy, including our own, sits on one strand of this vast network. The Milky Way is not isolated. It is embedded in a filament, connected gravitationally to structures far beyond what we can see with the naked eye. This connection is invisible in the night sky. It reveals itself only through careful mapping and deep observation. But it is real. The birth of the cosmic web teaches a subtle lesson. Complexity does not require complexity at the outset. Given time, simple beginnings can evolve into intricate patterns beyond immediate comprehension. The universe did not need intention to create structure. It needed imbalance and patience. From near uniformity emerged a vast lattice of matter and emptiness, binding galaxies into a coherent whole while leaving most of space almost entirely empty. The cosmic web stands as a reminder that the universe's grandest designs are not imposed. They are grown slowly, quietly, and inevitably out of the simplest possible beginnings. In art and architecture, there is a concept that is easy to overlook but impossible to ignore once understood. Negative space. It is the empty area around a subject, the silence between notes, the blank margin that gives form meaning. Without it, shapes blur, compositions collapse, and nothing stands out. The universe follows the same principle. Cosmic voids are not merely the absence of galaxies. They are the negative space that defines everything else. Without them, the cosmic web would lose its structure. Filaments would dissolve into noise. Clusters would have no edges. Meaning itself would flatten. This reframing changes how emptiness is interpreted. Voids are no longer passive leftovers between interesting regions. They are active participants in shaping the geometry of the cosmos. When astronomers first saw large-scale maps of galaxies, what stood out were not the galaxies themselves, but the spaces between them. The eye naturally traced the filaments because the voids carved them into visibility. The web became legible precisely because most of space was empty. This is not a visual trick. It is a physical reality. The universe organizes matter into contrast. Dense regions only appear dense relative to their surroundings. In a uniformly filled cosmos, there would be no clusters, no walls, no filaments, only mild variations, lost in sameness. Structure requires emptiness to exist alongside matter. Voids provide that contrast on the largest possible scale. They act as boundaries without walls, defining regions without containing them. A void does not push matter outward like a force. Instead, its existence reflects where matter has already moved away. The shape of a void is therefore a record of motion, a fossilized imprint of gravitational history. In this sense, voids are not empty spaces waiting to be filled. They are finished products of cosmic evolution. Their geometry carries information. Round voids suggest relatively isolated evolution. Elongated voids reveal the pull of nearby filaments. Interconnected voids trace the merging history of underdense regions over billions of years. Nothing in their shape is arbitrary. Negative space also influences perception of scale. When you see a massive galaxy cluster, its size feels impressive only because it sits against a backdrop of emptiness. Remove the voids, and scale collapses. Everything becomes crowded, compressed, indistinct. This has observational consequences. Astronomers rely on voids to identify the edges of structures. The transition from underdense to overdense regions marks where one filament ends and another begins. Voids serve as natural coordinate systems in an otherwise featureless expanse. They help define where here ends and there begins. Voids also simplify complexity. Dense regions are chaotic. Galaxies interact, merge, explode, and feed back energy into their surroundings. Interpreting these environments requires untangling many overlapping processes. Void interiors, by contrast, are comparatively clean. Few interactions occur. Evolution proceeds slowly. This simplicity allows astronomers to isolate fundamental effects that are buried elsewhere. In this way, negative space becomes clarity. There is another, deeper implication. Voids reveal that the universe is not built like a solid object placed into empty space. It is built like a pattern emerging from space itself. Matter does not fill space, it traces it. Space is primary, matter is secondary. This inversion challenges everyday intuition. Humans tend to think of space as a container, an empty box in which objects reside. Cosmology suggests the opposite. Space has structure, and matter responds to it. Voids make this visible. In dense regions, space-time curvature is strong. In voids, it is weaker. This difference shapes how time passes, how light travels, and how expansion unfolds. The negative space is not uniform. It has gradients, histories, and consequences. Even the expansion of the universe becomes easier to understand through this lens. Expansion does not occur evenly everywhere. It proceeds differently in dense regions versus empty ones. Voids, being less resistant to expansion, grow faster. They stretch space more freely. As voids expand, they accentuate the contrast that defines the cosmic web. The negative space becomes more negative. The positive space becomes more confined. The pattern sharpens. This feedback loop is subtle but relentless. From a philosophical perspective, voids challenge the instinct to equate importance with presence. In many human systems, absence is treated as failure, lack, or deficiency. The universe does not share that bias. Here, absence is functional. The most common environment in the cosmos is not a galaxy, a star, or a planet. It is a void. Most of space exists in a state of extreme sparsity. Any account of the universe that ignores this fact is incomplete by definition. This realization can feel unsettling. It places humanity firmly on the margins of typical cosmic conditions. We live in an exception, not the rule. Our galaxy is a rare island in an ocean of nothing, but it also offers perspective. The cosmic web is intelligible because of voids. The universe is readable because emptiness outlines form. Without negative space, there would be no narrative to extract from the data, only noise. Even the act of measurement depends on this contrast. Distance indicators, clustering statistics. Lensing measurements all rely on variations against a background. Voids provide that background. They are the silence that allows the signal to be heard. There is an aesthetic truth here as well. The universe's beauty does not come solely from its luminous objects. It comes from the balance between presence and absence, between light and dark, between structure and emptiness. This balance is not accidental. It is the inevitable outcome of simple physical laws operating over vast expanses of time. Voids are not mistakes waiting to be corrected. They are not gaps in an unfinished design. They are essential components of the cosmic composition. Like negative space in a painting, they guide the eye, define form, and give meaning to what is present. Remove them, and the universe loses its shape. In the end, cosmic voids teach a quiet lesson. Reality is not built only from things. It is built from relationships between what exists and what does not. The universe is not full in spite of its emptiness. It is structured because of it. Light feels simple. It moves in straight lines, at a constant speed, indifferent to what lies between its source and your eyes. In everyday life, empty space is merely the absence of obstacles. Light crosses it without consequence. In the universe, that assumption fails. When light travels across cosmic distances, it does not move through emptiness as if emptiness were neutral. Even the most underdense regions, cosmic voids, shape its journey in subtle but measurable ways. The path light takes, the energy it carries, and the story it tells are all influenced by the nothingness it passes through. This is not because voids contain objects to block light. It is because space itself is not passive. According to modern physics, light does not travel through space in the way a bullet travels through air. It follows the geometry of space-time. Wherever space-time is curved, stretched, or evolving, light responds. Dense regions curve space-time strongly. Galaxies and clusters bend light, magnify distant objects, and distort images through gravitational lensing. These effects are dramatic and easy to visualize. Voids do something quieter. Inside a void, space-time curvature is weaker. There is less mass to warp geometry. As a result, light experiences fewer gravitational detours. It travels along paths that are closer to straight, not because nothing happens, but because less happens. Over short distances, this difference is negligible. Over hundreds of millions or billions of light years, it accumulates. Light does not simply cross voids unchanged. One of the key effects involves gravitational redshift. When light climbs out of a gravitational well, it loses energy and shifts toward longer wavelengths. When it falls in, it gains energy. Clusters create deep wells. Voids create shallow ones. As light enters a void, it falls into a region of lower gravitational potential. As it exits, it climbs back out. In a perfectly static universe, these effects would cancel exactly. The universe is not static. Because cosmic voids expand faster than dense regions, the gravitational landscape changes while light is passing through. This creates a subtle energy imbalance known as the integrated Sachs-Wolf effect. Photons gain or lose a tiny amount of energy depending on how the void evolves during their journey. Individually, the effect is minuscule. Collectively, across millions of photons, it becomes detectable. This means voids leave fingerprints on the oldest light in the universe, the cosmic microwave background. Regions of the sky corresponding to large voids show slight temperature shifts, not because the voids emit radiation, but because they alter the energy of light passing through them. Nothing leaves a mark. Light also responds to the expansion rate of space. Inside voids, where matter offers little gravitational resistance, space stretches more freely. Light traveling through these regions experiences a slightly different expansion history than light skirting dense structures. This difference alters how distances are inferred. When astronomers measure the brightness of distant objects or the apparent size of standard rulers, they assume an average expansion along the line of sight. But if that line of sight passes predominantly through voids, the inference can be biased. The universe can appear to expand faster along emptier paths. This does not mean measurements are wrong. It means they are sensitive to environment. Another subtle consequence involves time delay. Light passing near massive objects takes longer to arrive than light passing through emptier space, even if the geometric distance is the same. This is known as gravitational time delay. Voids minimize this delay. When comparing multiple paths light can take, such as in gravitational lensing systems, paths through voids arrive slightly sooner. Over cosmic distances, these differences help reconstruct the mass distribution of the universe. Again, emptiness participates. There is also the question of angular distortion. Dense regions shear light bundles, stretching images tangentially. Voids do the opposite. They slightly defocus light, reducing convergence. The effect is weak, but measurable in large statistical samples. This anti-lensing effect allows astronomers to map voids indirectly. By measuring how background galaxies appear subtly less distorted in certain regions, researchers infer the presence of large, underdense structures. Voids are detected not by what they emit, but by how they fail to distort light. Perhaps the most important implication is methodological. Almost everything we know about the distant universe comes from light that has crossed enormous expanses of space. That space is mostly empty. The properties of emptiness, therefore, influence nearly every cosmological observation. Ignoring voids would mean misinterpreting the messenger. For decades, cosmology treated light propagation as something that happened between objects. Now it is understood as something that happens through an evolving medium space-time, shaped by both matter and its absence. This realization has forced refinements in precision cosmology. Models now account for line-of-sight environments. Simulations track photons through realistic distributions of voids and filaments. Emptiness is no longer averaged away. There is an irony here. The clearest images of the distant universe often come from light that has traveled primarily through voids. These paths avoid dense regions that would otherwise scatter, lens, or delay photons. In this sense, voids act as transparent corridors through the cosmos. The emptiest places offer the cleanest views. From a broader perspective, this reframes how information travels in the universe. Light does not simply reveal distant objects. It reveals the space between them. Every photon carries a record, not only of where it started, but of what it encountered or did not encounter along the way. Cosmic voids, silent and invisible, imprint themselves on this record. This challenges a deeply ingrained intuition. That absence leaves no trace. In cosmology, absence shapes trajectories, shifts energies, and biases conclusions. Light is the universe's historian. Voids are chapters written in faint ink. When astronomers decode the light reaching Earth, they are not just reconstructing distant galaxies. They are reconstructing the structure of nothingness itself. The darkness between the lights becomes part of the story. In the end, light teaches a counterintuitive lesson. To understand what we see, we must understand what the light passed through. And most of what it passed through was not matter, not stars, not galaxies, but vast regions where almost nothing was there. The journey through nothingness matters. Cosmic expansion is often described as a single, uniform process. Space stretches, galaxies move apart. The universe grows larger everywhere at once. That description is accurate and incomplete. On the largest scales, the universe expands, but on smaller, structured scales, that expansion does not unfold evenly. Matter resists it, gravity slows it, and where matter is scarce, expansion proceeds more freely. Cosmic voids make this difference visible. Inside a void, there is little mass to pull space inward. Gravity's braking effect is weak. As a result, space in these regions stretches faster than it does in denser environments. The expansion rate is not globally uniform in practice, even if it is governed by universal laws. This is a subtle point, but a crucial one. Expansion is not something that happens to galaxies alone. It happens to space itself, and space responds differently depending on what occupies it. Where matter is dense, expansion is suppressed or even halted locally. Where matter is sparse, expansion accelerates. Voids are therefore not just empty regions. They are fast lanes of cosmic expansion. This does not mean voids are exploding outward. Nothing is being pushed. Instead, the absence of mass allows the natural stretching of space to proceed with less resistance. Over billions of years, this difference accumulates. The consequence is geometric. As voids expand faster, they grow larger relative to dense regions. Filaments thin, clusters become more isolated. The cosmic web sharpens its contrast. Emptiness grows emptier. Structure becomes more confined. This process is gradual but relentless. From within a dense region like a galaxy cluster, this behavior is easy to miss. Local gravity dominates perception. Expansion feels irrelevant. Galaxies are bound. Distances remain stable. But from a broader perspective, voids quietly reshape the global layout of the universe. This uneven expansion has observational consequences. When astronomers measure cosmic distances, they rely on light that has traveled through space for millions or billions of years. Along its journey, that light passes through a patchwork of environments, clusters, filaments, and voids. Each region contributes differently to the overall expansion experienced by the photon. A path dominated by voids samples faster expanding space. A path dominated by dense regions samples slower expanding space. The inferred distance depends on the balance between the two. This does not introduce random noise. It introduces systematic variation. If large-scale surveys observe many objects along lines of sight that preferentially cross voids, the measured expansion rate can appear slightly higher. If observations are biased toward denser environments, the rate can appear lower. The universe does not expand differently for different observers, but it can appear to, depending on where and how measurements are made. This realization complicates a long-standing assumption in cosmology, that averaging over large enough volumes smooths out local differences. Voids challenge that assumption because they dominate volume. Most of space is underdense. The average universe is closer to a void than to a cluster. This has led researchers to re-examine how average expansion should be defined. Should it be weighted by volume or by mass? These choices are equivalent in a perfectly uniform universe. In a universe dominated by voids, they diverge. The difference is not philosophical. It is measurable. Simulations that track expansion locally show that void interiors can expand significantly faster than the cosmic mean over time. This leads to an effective stretching of large-scale distances that differs slightly from simple models. These deviations are small, percent level or less, but modern cosmology operates precisely in this regime. Precision turns small effects into serious considerations. Void expansion also affects how structures evolve. As voids grow, they exert pressure on their boundaries not through force, but through geometry. The faster expansion inside pushes matter toward the edges, reinforcing filaments and walls. Structure formation becomes increasingly asymmetric. Dense regions resist expansion. Empty regions amplify it. This feedback loop accelerates the segregation of matter and emptiness. The cosmic web becomes more skeletal with time. There is also a temporal aspect. In the early universe, matter density was higher everywhere. Differences between dense and empty regions were smaller. Expansion behaved more uniformly. As the universe aged and matter diluted, voids became more dominant. Their influence on expansion grew. This means the role of voids in shaping expansion is not constant. It increases with time. This temporal evolution matters when interpreting observations at different distances. Distant objects reveal the universe as it was long ago. When voids were less developed, nearby observations sample a universe where voids are larger and emptier. Comparing the two requires care. Failure to account for this evolution can create apparent discrepancies. The universe may look like it is expanding differently at different epochs, not because the underlying physics changed, but because the spatial distribution of matter did. Voids amplify this effect. From a conceptual standpoint, this challenges the idea that expansion is a single number describing the entire cosmos. Expansion is better understood as a process that emerges from the interplay between matter and space. In regions dominated by matter, gravity shapes evolution. In regions dominated by emptiness, geometry takes the lead. Neither regime tells the full story alone. This perspective also reframes the role of dark energy. Dark energy is often invoked as a uniform driver of accelerated expansion. Voids provide an environment where acceleration appears naturally enhanced. Even without invoking new components, this does not eliminate the need for dark energy, but it complicates how its effects are interpreted observationally. The universe's behavior is not dictated solely by what exists. It is dictated by how existence is distributed. From a human perspective, this is unsettling. We prefer simple narratives, one expansion rate, one cosmic story. Voids refuse that simplicity. They insist that context matters, that location matters, that emptiness is not neutral. When astronomers say the universe is expanding, they are describing a global truth. When they measure how fast, they are sampling a local reality shaped by structure and absence. Cosmic voids remind us that even the most fundamental processes look different depending on where you stand. Expansion is not wrong in empty regions. It is revealed. The emptiest places do not contradict the universe's laws. They expose their nuances. Every measurement is made from somewhere. In everyday life, that fact is trivial. In cosmology, it becomes unsettling. When astronomers describe the universe, they often speak as if observations are made from a neutral vantage point, as though Earth were an interchangeable coordinate with no special influence on what is measured. The laws of physics are assumed to be the same everywhere, and on the largest scales. That assumption holds. But measurements are not laws. Measurements depend on position, and the question cosmic voids force us to confront is uncomfortable. What if where we are subtly shapes what we think the universe is doing? At first glance, the idea sounds dangerous. It brushes against an old taboo in cosmology, the fear of returning to a special place argument, where humanity's location is treated as privileged. Modern cosmology was built in opposition to that idea. Earth is not the center. The sun is not special. The Milky Way is one of billions. Yet rejecting specialness does not mean rejecting environmental context. The universe is not uniform on all scales. It is structured. Galaxies cluster. Matter flows. Voids dominate volume. And we do not observe from an average location, we observe from inside a galaxy, embedded in a filament, near the edge of large underdense regions. That alone is not controversial. What is controversial is whether this environment can bias our measurements in subtle, cumulative ways. Consider how cosmic distances are measured. Light from distant objects travels through vast expanses of space before reaching Earth. Along the way, it passes through regions of different density clusters, filaments, voids. Each region influences expansion, gravitational potential, and light propagation slightly differently. If most of the light we observe travels through emptier than average space, then the expansion history inferred from that light may reflect void-dominated geometry rather than a true cosmic mean. This is not a hypothetical concern. On large scales, voids occupy most of the universe's volume. A random line of sight is more likely to pass through emptiness than through dense matter. From a volumetric standpoint, emptiness is the norm. This raises a subtle asymmetry. The average observer defined by volume does not live in a typical galaxy environment. Observers live where matter exists. Measurements, however, sample where matter does not. This mismatch matters. In a perfectly homogeneous universe, it would not. But in a universe with strong contrast between dense and empty regions, averaging becomes ambiguous. Do you average by mass or by volume? Do you define typical conditions by where matter resides or by where space resides? These questions are not philosophical. They affect how data is interpreted. Some researchers have explored models in which our local environment, a filament near the boundary of large voids, could slightly bias measurements of cosmic expansion. The effect would be small, but persistent. Over many observations, it could mimic or amplify apparent acceleration. This idea does not require exotic physics. It relies only on geometry and structure. Crucially, this does not imply that we are at the center of the universe. It implies something subtler, that the universe is lumpy enough that location influences inference. Even if the laws remain universal, this distinction is often misunderstood. Saying, our measurements may be biased by our environment, is not the same as saying, the universe revolves around us. It is saying that observational context matters in a structured cosmos. Astronomers already accept this principle on smaller scales. Measuring the motion of nearby galaxies requires correcting for local gravitational flows. Measuring the cosmic microwave background requires subtracting the motion of our galaxy relative to the cosmic frame. Environmental correction is routine. The question is whether similar corrections are needed on much larger scales. Historically, cosmology assumed that beyond a certain distance, local effects average out. Void-dominated volume challenges that assumption. Because voids are so large and so common, their influence may not cancel cleanly. This realization has prompted a re-evaluation of how cosmic averages are defined. Some approaches weight averages by mass, emphasizing dense regions. Others weight by volume, emphasizing voids. These approaches yield slightly different expansion histories. Neither is wrong. They answer different questions. Mass-weighted averages describe how matter behaves. Volume-weighted averages describe how space behaves. In a universe where space is mostly empty, those perspectives diverge. From inside a galaxy, we naturally adopt the mass-weighted view. Observations, however, often probe the volume-weighted reality. This mismatch is subtle, but it accumulates. The most provocative versions of this idea once suggested that cosmic acceleration itself could be an illusion caused by large-scale inhomogeneity. Most of those extreme models have been ruled out by data. The effects are not large enough. But the underlying lesson remains. Even small environmental biases matter in precision cosmology. When measurements aim for percent-level accuracy, ignoring where observations come from is no longer safe. Void-related bias does not overthrow cosmology. It refines it. It forces a shift from assuming idealized uniformity to grappling with a universe that is statistically homogeneous but locally complex. The distinction is critical. Homogeneous does not mean smooth. It means uniform only when averaged over sufficiently large scales. The challenge is defining what sufficiently large means in a universe dominated by voids hundreds of millions of light-years across. This tension between principle and practice is where cosmology becomes most human. Scientists are not measuring an abstract universe. They are measuring this universe from this location. Using this distribution of light paths, every conclusion carries that imprint. Cosmic voids sharpen this awareness. They expose the gap between theoretical symmetry and observational reality. Rather than undermining confidence in cosmology, this awareness strengthens it. It replaces naive assumptions with explicit modeling. It acknowledges limitations without surrendering rigor. The universe does not deceive us, but it does demand humility. Measurements are not made from nowhere. They are made from a specific place in a structured cosmos. Recognizing that fact does not diminish our understanding, it deepens it. Our location may not define the universe, but it does shape how we come to know it. Few ideas make cosmologists more uneasy than the suggestion that our location might be unusual in a way that matters. Not because it is obviously wrong, but because it threatens a foundational habit of thought, the assumption that, on large scales, where we are does not significantly influence what we infer about the universe. The notion that we might live near a large cosmic void presses directly against that habit. At first hearing, it sounds like a step backward. For centuries, science has worked to dismantle the idea that humanity occupies a privileged position. Earth is not the center. The sun is not special. The Milky Way is one among countless galaxies. Each demotion was a triumph of perspective. So when researchers raise the possibility that our cosmic neighborhood could subtly affect measurements, the reaction is often defensive. It feels uncomfortably close to reviving an old error. But the idea is not about privilege. It is about geometry. Cosmic voids are enormous. Some span hundreds of millions of light-years. They are not rare anomalies. They dominate the volume of the universe. Living near a void does not mean living at a cosmic bullseye. It means existing in a structured universe where dense regions naturally border emptier ones. And that is exactly where galaxies tend to be. Galaxies do not form in void centers. They form along filaments and walls, the boundaries between emptiness and density. If you live in a galaxy, you almost certainly live near a void. The controversy is not proximity. The controversy is scale. Could the voids near us be large enough, coherent enough, and influential enough to bias certain measurements? This question gained traction when cosmologists began comparing precise observations across different distance scales and noticing small but persistent discrepancies. The differences were not dramatic. They were subtle, and subtlety is where systematic effects hide. Some models explored the idea that if we reside in or near a particularly large, underdense region, local expansion could be slightly faster than the cosmic mean. Light traveling outward would sample faster expanding space before reaching denser regions farther away. To an observer inside that region, distant galaxies could appear to recede faster than expected. The universe would not actually be expanding differently everywhere. It would only appear that way from our location. This is where discomfort sets in. The idea does not violate physics. It does not require new forces or exotic particles. It relies only on known behavior. Gravity slows expansion where matter is dense. Expansion proceeds more freely where matter is sparse. What makes it controversial is not its mechanics, but its implication, that inference depends on environment. Critics of the idea are quick to point out its limits. For such an effect to be significant, the void would have to be enormous and unusually symmetric. Observational evidence places strong constraints on how large such a structure could be without conflicting with other data. Most extreme versions of the idea have been ruled out. But ruling out extremes does not eliminate the underlying concern. Even smaller environmental effects matter when cosmology aims for precision. When measurements strive for accuracy at the percent level, Assumptions that were once harmless become liabilities. The debate is therefore less about whether we live inside a void, and more about how void-rich our observational environment is. The universe does not offer a clean laboratory. It offers a landscape. Another reason the idea provokes resistance is sociological. Cosmology is built on the Copernican principle, the idea that we do not occupy a special position. This principle has been extraordinarily successful. It has guided interpretations and constrained models. But principles are not laws. They are assumptions that must be tested, not protected. Living near a void does not violate the Copernican principle if such environments are typical for galaxies. The discomfort arises only if typical is defined ambiguously by volume rather than by where observers can exist. Most of the universe's volume is empty. Most observers exist in dense regions. Those two facts coexist without contradiction, but they complicate averaging. The controversy, then, is not about centrality. It is about sampling bias. Astronomers do not choose where to observe from. They inherit a location. From that location, they sample the universe along particular lines of sight, through particular distributions of structure. If those distributions are not statistically neutral, measurements reflect that fact. This does not make cosmology subjective. It makes it contextual. There is also a psychological dimension. Voids feel like absence, and absence feels unimportant. It is counterintuitive to imagine that what is missing could influence what is measured, yet the previous sections have already undermined that intuition. Voids affect light propagation. They affect expansion locally. They dominate volume. Ignoring them because they feel like nothing is no longer defensible. The controversy persists because the effects are small and difficult to isolate. They sit at the edge of detectability, tangled with other uncertainties. This makes definitive answers elusive, but elusiveness is not irrelevance. The debate has had a healthy consequence. It has forced cosmologists to model the universe more realistically. Idealized uniformity is no longer taken for granted. Inhomogeneity is treated as a feature, not a nuisance. This shift has improved simulations, sharpened interpretations, and clarified where assumptions enter analyses. In that sense, the idea of living near a void has already done valuable work, even if its strongest versions are false. It has reminded the field that the universe we describe is not the universe as imagined from nowhere. It is the universe as seen from here. That recognition does not weaken cosmology. It matures it. There is also a quieter philosophical lesson. The discomfort surrounding this idea reveals how deeply humans want to be irrelevant to the cosmos, to observe without influencing interpretation. That desire is understandable. It feels safer. But the universe does not promise safety. It offers structure, complexity, and context. Living near a void does not make us special. It makes us situated, and being situated is unavoidable. The controversy is therefore not about whether the idea is embarrassing or elegant. It is about whether cosmology is willing to confront the consequences of a universe that is profoundly structured. Even on the scales where we once assumed smoothness, void or not, the lesson stands. Where you observe from matters, not because the universe revolves around you, but because reality is not uniform enough to pretend otherwise. That is not a return to old thinking. It is a refinement born from seeing the cosmos more clearly than ever before. Dark energy entered cosmology as a surprise. In the late 1990 seconds, observations of distant supernovae revealed that the universe is not merely expanding, but accelerating. Galaxies are not just drifting apart, they are doing so at an increasing rate. The simplest explanation was unsettling. Some unknown component, permeating all of space, is pushing the universe outward. This invisible driver became known as dark energy. From the beginning, dark energy was treated as something uniform, smooth, and omnipresent. Unlike matter, it does not clump. Unlike radiation, it does not thin out quickly. It appears to act everywhere, all the time, with the same strength. Cosmic voids complicate that picture. Voids are the emptiest regions of the universe, the places where matter's influence is weakest and space is most free to expand. If dark energy exists as a property of space itself, then voids are where its effects should be most exposed. This makes voids a natural testing ground for understanding dark energy's true nature. In dense regions, gravity dominates. Matter pulls inward, suppressing expansion. Any effect from dark energy is partially hidden, masked by the overwhelming presence of mass. In voids, that mask is removed. Expansion proceeds with minimal resistance. Voids exaggerate whatever is driving cosmic acceleration. This leads to a subtle but powerful question. Are we correctly separating the effects of dark energy from the effects of emptiness? In standard cosmology, accelerated expansion is attributed to dark energy acting uniformly. Voids are treated as consequences of structure formation, not as contributors to acceleration. But when expansion is measured locally, voids naturally appear to expand faster. This does not mean voids cause acceleration, but it does mean they can mimic aspects of it. If light from distant objects travels primarily through voids, the inferred expansion history will reflect the faster expansion of those regions over large samples. This can bias measurements in ways that resemble the influence of dark energy. The distinction is delicate. Dark energy is global. Void-driven effects are environmental. Separating the two requires careful modeling, not intuition. Early on, some researchers speculated that cosmic acceleration might be an illusion created by large-scale inhomogeneity, that voids could explain the observations without invoking dark energy at all. These ideas were provocative, but most have not survived confrontation with data. The effects of voids alone are not strong enough to account for the full acceleration observed, but dismissing them entirely misses the point. The failure of extreme models does not imply that voids are irrelevant. It implies that they are part of a more nuanced story. Dark energy may exist, but its observational signature is filtered through a universe dominated by emptiness. Void-rich geometry modifies how dark energy is perceived. This realization has reshaped how cosmologists think about testing dark energy theories. Instead of focusing only on dense regions or averaged quantities, attention has shifted toward environments where dark energy's influence should stand out most clearly. Voids are ideal for this purpose. Because voids contain little matter, they reduce the complexity of astrophysical processes. There are fewer galaxies, fewer feedback effects, fewer confounding variables. What remains is large-scale geometry and expansion. This makes voids sensitive probes of how expansion behaves when gravity steps back. Some dark energy models predict subtle deviations from standard behavior that become more pronounced in low-density environments. Modified gravity theories, for example, often include screening mechanisms that suppress deviations in dense regions but allow them to emerge in voids. If gravity behaves differently than expected, voids are where that difference should appear first. In this way, voids act like stress tests for cosmological models. They push theories into regimes where assumptions are exposed. Observationally, this has led to new strategies. Instead of treating voids as gaps to be averaged over, astronomers analyze them directly. They measure how voids grow, how their shapes evolve, and how light propagates through them. These measurements place constraints on dark energy that are complementary to those from supernovae or the cosmic microwave background. The results so far are consistent with dark energy, behaving much as standard models predict. But consistency is not closure. Precision matters. As measurements improve, even small deviations could become significant. Void-based analyses add an independent line of evidence, reducing reliance on any single observational method. There is also a conceptual shift underway. Dark energy is often described as a substance-filling space. Voids force a reconsideration of that metaphor. If dark energy is a property of space-time itself, then its effects are inseparable from geometry. Expansion is not something layered on top of structure, it is shaped by structure. In this view, dark energy does not act in isolation. It interacts with the distribution of matter by responding to where matter is absent. Voids are not just empty containers for dark energy to operate in. They are regions where the balance between expansion and gravity is tilted, revealing how that balance works. This reframing has philosophical implications. It suggests that cosmic acceleration is not a uniform push applied equally everywhere, but an emergent phenomenon whose appearance depends on how space is partitioned between dense and empty regions. Dark energy may still be real, but its story cannot be told without voids. There is also a cautionary lesson here. When cosmology speaks of mystery, it often means that existing concepts are stretched beyond their comfort zone. Dark energy is mysterious not only because we do not know what it is, but because it challenges how we think about space, time, and emptiness. Voids sit at the heart of that challenge. They remind us that most of the universe is not made of things, but of space itself. If space has properties, if it expands, accelerates, carries energy, then understanding the universe requires understanding space where it is least disturbed. That means studying nothing. Cosmic voids transform dark energy from an abstract parameter into a tangible question about geometry. They ask whether acceleration is imposed or revealed, fundamental or contextual. The answer is not yet complete. What is clear is that voids are no longer peripheral to the mystery of dark energy. They are central to it. They provide the cleanest stage on which expansion performs. Stripped of the distractions of matter, in the emptiest places in the cosmos, the question of why the universe accelerates becomes hardest to ignore and most honest to confront. In physics, few phrases carry as much weight as new physics. I know, it implies that the existing framework tested, refined, and trusted has reached its limits. Something fundamental is missing. A deeper rule is waiting to be discovered. But history offers a cautionary pattern. Before new physics is confirmed, reality often reveals a simpler truth. What looked revolutionary was sometimes a misunderstanding of context. Cosmic voids sit precisely at this crossroads. As measurements of the universe became more precise, small discrepancies began to appear. Expansion rates, inferred from different methods, did not align perfectly. Light behaved in ways that required careful correction. Geometry seemed to matter more than expected. These tensions sparked speculation about new particles, new forces, and modifications to gravity itself. All reasonable possibilities, but there was another option less dramatic, more unsettling. What if emptiness itself could imitate new physics? This idea does not suggest that physics is wrong. It suggests that physics applied to an oversimplified picture of the universe can produce misleading conclusions. The laws may be correct, but the assumptions about where and how they are applied may not be. The standard cosmological model relies heavily on averaging. On large enough scales, matter is assumed to be smoothly distributed. Small inhomogeneities are treated as noise that cancels out. Expansion is described by a single, global history. Cosmic voids challenge that logic. Voids are not small perturbations. They dominate volume. They are coherent, structured, and evolving. Treating them as statistical background may erase effects that do not average away cleanly. In such a universe, some signals that look like new physics may instead be emergent effects of geometry. Consider expansion again. If light from distant galaxies travels preferentially through voids, it experiences faster local expansion and weaker gravitational resistance. The inferred distance redshift relationship can shift subtly over large samples. This shift can resemble an acceleration beyond what simple models predict. To an observer, the data may suggest an additional energy component or modified gravity, but the underlying cause could be emptiness. This is not speculation without grounding. Numerical simulations that model realistic distributions of voids and filaments show that local expansion rates vary significantly across environments. When observations are interpreted assuming uniformity, these variations can bias results. The effect is small but precision. Cosmology lives in the small. Another example involves gravitational lensing. Standard lensing theory predicts how light bends around mass. In dense regions, the effect is strong and well understood. In underdense regions, the opposite occurs. Light is slightly defocused. This anti-lensing subtly alters the statistical properties of observed galaxy shapes. If not properly modeled, these effects can be mistaken for changes in fundamental parameters. Emptiness alters signals without introducing new forces. There is also the issue of time evolution. Voids grow with time. They expand faster than average. Their influence on light and geometry increases as the universe ages. Observations probing different epochs therefore sample different void regimes. If this evolution is not fully accounted for, it can create the illusion that cosmic behavior changes with time in unexpected ways. New physics is often invoked to explain such trends. Sometimes, the trend reflects structure. This does not mean new physics is off the table. It means the bar for claiming it must be high. Cosmology has reached a stage where environmental effects are no longer negligible. The universe is not a smooth backdrop with small ripples. It is a deeply structured system where emptiness is the dominant state. Ignoring that fact risks mistaking context for cause. The temptation to invoke new physics is understandable. It is exciting. It promises breakthroughs. It captures imagination. But history warns against premature conclusions. The precession of Mercury's orbit was not explained by emptiness. It required general relativity. But many other anomalies once thought profound vanished with better modeling, better data, or better understanding of environments. Cosmic voids demand similar restraint. They offer an explanation that is neither conservative nor radical, but corrective. They ask whether existing physics, applied to a more realistic universe, might already contain the answers we seek. This reframing shifts the role of theory. Instead of asking, "What new ingredient do we need?" it asks, "What did we overlook?" Instead of extending equations, it refines their domain. There is also a methodological lesson here. Precision cosmology cannot rely solely on elegance. It must confront complexity. The universe is not arranged to suit our simplifying assumptions. It is arranged according to gravity, expansion, and time indifferent to convenience. Voids embody that indifference. They are messy to model, difficult to observe directly, and uncomfortable to interpret. But they are real, and their effects are measurable. Treating them seriously does not undermine the search for new physics. It strengthens it. It ensures that when new physics is claimed, it is not standing on the shoulders of neglected structure. There is a deeper philosophical implication. Physics often advances by identifying what cannot be explained, but it also advances by recognizing when explanation has been misplaced. Emptiness teaches humility. It reminds us that absence can be as influential as presence. The universe may not need new rules to appear strange. It may only need us to look more carefully at what we thought was nothing. In that sense, cosmic voids act as mirrors. They reflect the assumptions built into our models. They reveal where averaging hides meaning. They expose the cost of convenience Can emptiness mimic new physics? In some cases, yes, not by breaking laws, but by revealing how those laws play out in a universe far more structured and far more empty than early cosmology ever assumed. And that realization may be just as transformative as discovering something entirely new. Cosmic voids began as an inconvenience. Blank regions on maps, missing data, awkward gaps between the things astronomers expected to matter. Over time, they became unavoidable, then indispensable, and eventually instructive, not just scientifically but conceptually. Voids force a reconsideration of what structure actually is. For much of astronomy's history, structure meant accumulation, stars gathering into galaxies, galaxies into clusters, clusters into superclusters. More matter meant more importance, density meant relevance. Voids overturn that hierarchy. They reveal that structure is not defined solely by what is present, but by contrast, a filament is a filament only because a void borders it. A cluster is dense only because most of the surrounding space is not. Without emptiness, density loses meaning, structure, it turns out, is relational. This insight seems obvious in retrospect, yet it runs against a deep cognitive bias. Humans are trained to focus on objects. We name them, classify them, admire them. Space between objects feels secondary, passive, empty of information. The universe does not share this preference. On the largest scales, emptiness is not the exception, it is the rule. Galaxies are rare, clusters are rarer, voids are everywhere. Any honest description of cosmic structure must therefore begin with absence, not presence. This inversion changes how cosmic evolution is understood. Structure did not arise because matter gathered everywhere. It arose because matter did not gather in most places. Gravity amplified small differences, draining matter from vast regions and concentrating it along thin boundaries. The result was not a filled universe with holes, but a hollowed universe with edges. Voids are the primary outcome. Structures are the residue. This perspective reframes progress in cosmology. Instead of asking only how galaxies formed, we ask how emptiness grew. Instead of tracing the buildup of mass, we trace the evacuation of space. Both tell the same story from opposite sides. Voids also teach that simplicity can emerge from complexity. Their interiors are quiet. Few interactions occur. Evolution proceeds slowly. Compared to the chaos of clusters, voids are calm. This calm is not trivial. It strips away distractions. In voids, fewer astrophysical processes compete for attention. Gravity and expansion dominate. As a result, voids become places where fundamental behavior is easier to see, not harder. They are minimal environments that reveal maximal truths. There is a lesson here that extends beyond cosmology. Complex systems often hide their governing principles beneath layers of activity. Remove enough layers, and the rules become clearer. Voids do for the universe what silence does for music. They expose structure by removing noise. This analogy is more than poetic. In music, silence defines rhythm. In language, pauses shape meaning. In architecture, empty space gives form. In the cosmos, voids articulate structure. Meaning emerges from contrast. Voids also challenge how significance is assigned. Human culture often equates meaning with abundance, more resources, more activity, more presence. The universe contradicts this intuition. The most common environment is not bustling, but sparse. The dominant condition is not fullness, but near emptiness. And yet, from this emptiness, everything else is defined. This realization can be unsettling. It places human existence firmly in a statistical minority. We live in a dense pocket of matter, surrounded by vast regions that will never host stars, planets, or life as we know it. But it can also be clarifying. It reminds us that rarity does not imply insignificance. Life may be rare, but that does not diminish its value. Galaxies may occupy little volume, but they anchor the cosmic narrative. Meaning is not assigned by prevalence. Voids make that explicit. There is also a temporal lesson. Voids grow over time. As the universe expands and matter continues to drain into structures, emptiness becomes more dominant. The future universe will be even emptier than the present one. Structure is transient. Emptiness is persistent. This does not mean the universe is running down in a simple sense. It means the balance between presence and absence shifts with time. What is exceptional now may become even more exceptional later. Understanding this evolution reframes cosmic destiny. The far future is not a crowded collapse, but a stretched, diluted landscape where isolated islands of matter drift apart across expanding voids. Voids are therefore not just features of the present, they are signposts of the future. On a deeper level, voids also expose the limits of anthropocentric thinking. Human intuition is shaped by scales, where emptiness is rare and filled space is normal. On cosmic scales, that intuition fails. Cosmology succeeds precisely when it abandons those intuitions. Accepting voids as central rather than peripheral marks a maturity in scientific thought. It shows a willingness to let data, not comfort, dictate worldview. It also demonstrates how meaning in science often comes from recentering attention from objects to context, from things to relationships. There is a philosophical echo here. Meaning in human life is often sought through accumulation, achievements, possessions, experiences. But many traditions argue that meaning also arises through absence, through silence, restraint, and space. The universe seems to agree. Void-dominated structure suggests that what is missing can be as informative as what is present. That boundaries matter as much as contents. That context gives significance. This does not romanticize emptiness. Cosmic voids are not benevolent or purposeful. They are simply the outcome of physics applied relentlessly over time. But their implications reach beyond equations. They encourage a broader definition of structure, one that includes absence as a constructive element rather than a failure. In practical terms, this has reshaped cosmology. Voids are now tools. They are measured, classified, simulated, and used to test theories. They are no longer ignored. In conceptual terms, they have done something quieter and more enduring. They have expanded the idea of what counts. The universe is not a collection of things floating in nothing. It is a pattern carved out of space itself, where emptiness and matter co-create structure. Voids teach that meaning does not require fullness. It requires contrast. And in a universe where most of space contains almost nothing, understanding that contrast may be the most important lesson of all. It is tempting to think of the universe as a collection of things: stars, galaxies, nebulae, worlds, even its mysteries, black holes. Dark matter, dark energy are usually framed as entities waiting to be understood. This way of thinking feels natural, because human life unfolds among objects. We navigate by landmarks. We define meaning by what is present. The universe does not share that instinct. On its largest scales, the dominant feature is not matter, but absence, not structure, but the space between structures. Cosmic voids are not rare exceptions carved into an otherwise crowded cosmos. They are the rule. Everything else is the deviation. Living in such a universe forces a quiet reorientation of perspective. We exist inside a galaxy, which itself sits on a filament, bordering vast regions where almost nothing happens. Our cosmic address is precise and improbable. From that vantage point, The sky looks rich and full, but zoom out far enough, and our entire galaxy becomes a thin thread outlining emptiness. This is not a poetic exaggeration. It is a statistical fact. Most of the universe's volume will never host stars. Most regions will never glow. Most space will remain dark, cold, and sparse for all of cosmic time. The environments that produce complexity, chemistry, planets, life occupy a vanishingly small fraction of reality. And yet, those rare environments are where meaning emerges. This contrast reveals something essential about structure. Structure is not the default state of the universe. It is the outcome of imbalance. Gravity pulled matter away from vast regions, concentrating it into thin boundaries. Voids grew as matter fled. Filaments formed as residue. Galaxies emerged as byproducts. Nothingness shaped everything. This does not diminish the significance of matter. It reframes it. Matter is special precisely because it is scarce. Galaxies matter because most places have none. Life matters because most of the universe is lifeless. In a universe shaped by nothing, rarity becomes value. There is also a lesson here about scale and humility. Human intuition is tuned to filled spaces. A room without furniture feels empty. A city without people feels abandoned. We associate emptiness with absence of purpose. Cosmic voids reject that association. They are not failures of formation. They are essential components of the cosmic design. Without them, there would be no web, no contrast, no large-scale structure to study. The universe would be less legible, not more. Emptiness, in this context, is functional. Living in such a universe changes how questions are framed. Instead of asking only how structures form, cosmology asks why emptiness dominates. Instead of focusing solely on what exists, it studies what does not and what that absence does. This shift has consequences beyond astronomy. It suggests that understanding reality requires attention to background conditions, not just foreground events. It reminds us that systems are shaped as much by constraints and gaps as by components. It invites a broader definition of causality. In human terms, this can feel unsettling. We prefer narratives where action comes from agents, from forces we can name. Voids act without acting. They influence without exerting force. They shape outcomes by allowing space to stretch, light to travel, matter to flee. They are passive only in appearance. There is also a temporal dimension to living in a void-shaped universe. Emptiness grows with time. As expansion continues, voids expand faster than dense regions. Matter becomes more isolated. The future universe is not one of increasing complexity everywhere, but of increasing separation. Islands of matter will drift apart across expanding seas of nothing. This does not imply decay in a moral sense. It implies change in balance. The same processes that once created structure now gradually isolate it. The universe is dynamic, not directional. It does not aim for fullness or emptiness. It follows rules, understanding that helps strip cosmic evolution of unnecessary drama. The future is not catastrophic by default. It is sparse. There is a strange comfort in that. It suggests that the universe is not hostile or indifferent in a human sense. It simply is. Emptiness is not a threat. It is a condition. From our position inside a dense region, this condition is easy to forget. The night sky dazzles. Galaxies feel abundant. But this is a local illusion, born of perspective. Reality is quieter. Living in a universe shaped by nothing also reshapes how knowledge itself is valued. Much of cosmology's progress has come not from discovering new objects, but from recognizing patterns of absence. Voids forced astronomers to abandon assumptions of smoothness. They exposed the limits of averaging. They revealed where intuition breaks. In that sense, Voids have done what the best scientific discoveries do. They have changed how questions are asked. They have taught cosmology to look where nothing seems to be happening and to expect insight there. This lesson extends naturally to meaning. Humans often search for significance in accumulation, more data, more discoveries, more complexity. The universe suggests a different balance. Meaning arises not from filling every space, but from structure emerging against a backdrop of emptiness. The cosmic web is meaningful because voids outline it. Galaxies are meaningful because they are rare. Life is meaningful because the universe is overwhelmingly inhospitable. Nothingness does not negate meaning. It enables it. There is no requirement to romanticize this. Cosmic voids are not benevolent teachers. They do not care whether they are understood. Their lesson is incidental, not intentional, but it is still a lesson. The universe we inhabit is not shaped primarily by what exists, but by how existence is distributed. Space matters. Absence matters. Context matters. Living in such a universe does not reduce humanity to insignificance. It clarifies our position. We are not central. We are not typical. We are not surrounded by abundance. We are perched on a thin strand of matter, suspended in a vast architecture of near-nothingness. And from that unlikely position, we are able to see the whole. That may be the most striking consequence of all. In a universe dominated by emptiness, islands of matter become places where the universe can observe itself. The voids provide the silence. The structures provide the voice. Together, they tell the only story the cosmos has ever told, a story shaped not just by what is there, but by what is not.